I'm Piero, nice to meet you. I'm from Uber AI, which is the organization at Uber that develops machine learning and AI models, both platforms and research. And Ludwig, this platform that I built actually built it for myself to begin with, and I released it open source so that everybody can potentially take advantage of using it. So it's a toolbox for training deep learning models and using them for production without writing code. And it has a bunch of design principles that I tried to follow when I was actually designing it. First of all, I tried to strike a balance in terms of generality. So the toolbox actually allows you to cover many different machine learning use cases. Another design principle was flexibility. So I want both expert users and novices both to be able to use the tool and get some value out of it. The tool is also pretty extensible. We made it so that it's really easy to add additional models to Ludwig because the interfaces are really simple, and I'm going to show you an example of those. We try also to make the models understandable, at least in terms of what they're predicting and what's the quality of their predictions through a set of visualizations that are provided for you. We'd also try to make it as easy as possible to use. I'm going to show you, you don't need to write any code, but you also have some programmatic interfaces that are really, really easy to use, just a couple lines of code, and you can train a deep learning model. And finally, we release it as open source as an Apache 2 licensed project. So you are welcome to play around with it and also to contribute to it. All right. So let's start with an example. Let's assume of how Ludwig works. Let's assume you have a data set which is structured with two columns. One is this text, which is probably news, and the other column is class, which contains some different classes of all these news. What you can do with Ludwig is you can just run this simple command, Ludwig experiment, your CSV file containing that data, and a model definition that we're going to look into in detail. And what Ludwig does for you is it splits the data set in training, validation, and test. It trains on the training set, validates on the validation set, and predicts on the test set. As you can see, the model definition is basically a string in this case. That string can actually also be provided as a YAML file because it's actually more convenient when the model definition becomes bigger. And all you have to specify is one input feature and one output feature, and what is the type of that input feature and output feature, and what's the name. And the name is actually the name of the column in your CSV file. And what happens is, this is the output of the first epoch. So you can see like all the measures and also the loss for all the three different splits after the first epoch. Then things get better and they improve over the next epoch. So this is the fourth epoch, if I remember correctly, yes. And then at the 14th epoch, after 10 epochs where the score on the validation set didn't improve, there's early stopping, and the best model, the model at the fourth epoch, the one with the best validation accuracy, is going to be used to actually provide some predictions. And those predictions, this is some measures of the quality of those predictions that are overall over all the classes. And these are some examples of the measures of the quality of the predictions for each single class in your data set. Under the hood, the way it works is it separates the process in two steps, like many machine learning tools actually, in training and prediction phase. At training time, what happens is that you have your CSV file. It's going to be, there's a module that is performing some pre-processing that outputs some mappings. For instance, if you have classes, you have associated IDs to those classes, and you have this mapping, you saved it in a JSON file. And the pre-processed data is going to be provided to the model, and the model is going to be trained, and hyperparameters and weights are going to be saved. Then at prediction time, what happens is that you have some new data, and you map it into tensors in the same way you did it in the training time, by using the same mappings that you obtained at training time. And you also load the weights and the hyperparameters of the model. So this new data is going to be given to the model that is going to spit out some predictions. And those predictions are mapped back into the data space, again, through the mappings. And what I showed you before, the experiment command, what it's actually doing is it's performing first the training and then the prediction, one after the other. And it's going to save both the predictions labels, in this case, because those are classes, and some training statistics and test statistics. And those are going to be provided to the visualization module in order to obtain some visualization of all the performances of the model and the predictions of the model. So what's going on under the hood? The magic is basically it lies in three different things. The first thing is a data type abstraction that I'm going to tell you about that makes it so that you have really generic and reusable code. And the fact that you're providing a declarative YAML file that describes your model without the need to actually write code exactly, because it's all written for you. And finally, a smart use of KVArgs. If you're familiar with Python, KVArgs is a way to provide dictionaries as arguments with their values to functions. And that's actually heavily used inside Ludwig. So let's go back to our example from before. You have this model definition, and what is actually happening is that the model definition is going to be merged with some defaults. And this is actually the full model definition that you get. It's divided in 5 different sections. The first section is the input features, and the third section is the output features. Those two, we've already seen an example of that. And there's also a combiner section that I'm going to tell you about, and a training and pre-processing sections. These sections are there to provide you with the flexibility to specify all the upper parameters that you want. So let's focus on the first part. This is the overall architecture that you have in Ludwig. So each single input that you're providing to the model is actually is going to be encoded by an encoder, and the encoders change for each single data type. So when you specify the data type, you're going to have different encoders for each single data type. Then the information from all the input features is going to be combined, and the output of this combination is going to be provided to several different output decoders that are going to decode, depending on the data type, again, of the decoder, of the output feature, what is the model going to predict. And so this is a really general architecture that allows for many different instantiations for different machine learning problems. For instance, if you have an input text and an output class category, what you obtain is a text classifier. But if you have an image as input and text as output, what you're going to have is image captioning system, for instance. Or if you have several numerical, binary, and categorical features as input and one numerical feature as output, then you're performing a regression. And for instance, if you have an image and a text as input and a binary classifier as output, then what you're doing, you can see that this is like potentially a visual question answering system. So combining all different input data types and all different output data types allows you for building several different machine learning applications. Moreover, each single input data type and each single output data type can have different types of encoders and different types of decoders, which allows you for having a flexibility of changing the models that are actually performing the encoding and the decoding. For instance, for text, we have, actually the moment we have 5, the transformer is coming, it's like probably going to be there in the next week or so. So all these encoders go from raw data into vector representation, and they can all be changed one for the other, just changing one string. For example, if you want to use the parallel CNN in your model definition, you have to define just the first 4 parameters here. What is the name of the column in the CSV? What is the data type, in this case, text? What is the encoder that we want to use, in this case, parallel CNN? And what is the level if you want to make it work at the character level or at the word level? All the other parameters are optional, and an expert user can play around with it, can change the number of filters, can change the size of the fully connected layers, and so on and so on. But a novice can actually just specify those 4 parameters, and all the other ones are default. The defaults are going to be used, and model that already works can be obtained. And if you want, so basically all these parameters are mapped one-on-one with the parameters, arguments of the function that builds this object that contains this encoder. So that's where KVArgs is used, for instance. And if you want to use a different encoder, all you have to do is you have to change the keyword that you use for the encoder parameter. And all the other hyperparameters are going to be specific for the specific encoder, but you can have also a stacked parallel CNN or an RNN. All these are different encoders, just changing one string. And for instance, for the RNN, you can see that the hyperparameters that are defined there are much different from the ones for the CNN. Here you have the cell type. So for instance, you can have an LSTM or a GRU, if it's bidirectional or not, and so on. All these parameters are specific for the encoder. And also CNN or RNN, which is a combination of the two. This architecture also has the advantage that there's advantage of performing, like allowing you for a lot of code reuse. And for instance, the same encoders that I use for text can be used also for discrete sequences and for time series. And while for images, I only have 2 encoders at the moment. The first is like a stack of CNN, which is similar to VGG, and the second one is a ResNet, but many more can be added really easily. Other feature data types actually have a simpler way of, with less hyperparameters and just a simple one single encoder. For instance, categorical features can be either encoded as sparse one-hot encodings or dense vectors. Numerical features, they all have one neuron associated with them so that the neuron can learn to scale them, but basically they're just concatenated with all the other features, and binary features also, they're mapped exactly as they are. And also sets and bags features are allowed to use. And sets features, basically you're gonna have one embedding for each single element in the set, and those are gonna be aggregated. Bags features works in exactly the same way, but the aggregation function is weighted by the frequency of the elements in the bag. Then after you have all the information coming from all the different input encoders, there's a piece called combiner that combines this information. The most simple one is just taking all the vectors coming from all these encoders, concatenating them, and then running them through some fully connected layers. But there's other combiners that are also available. And the output of the combiners is actually provided to each single output decoder. And there's output decoders for all different data types. For instance, for category, which is the most developed one, which allows you to do multi-class classification. You can specify the loss, and you can specify all sorts of other parameters to the loss for you to tweak and to play around with. For numerical features, the ones that basically perform regression, you can have different losses like mean squared error and mean absolute error, and play around with those two. For binary features, there's binary cross entropy is going to be used. While for sequence features, this is like the most advanced part probably. If you're familiar with sequence-to-sequence models, this is basically the two-sequence part, the generation part. And what you have here is either a decoder which is a generator or a decoder which is a tagger. The generator performs the generation like in a sequence-to-sequence model. The tagger actually performs a classification for each single element of an input sequence. And we're going to see an example of that. The set feature actually allows you for multi-label classification. And finally, if you have multiple features that interact with each other, one feeding into the other in terms of information, you can specify dependencies among them, and a directed acyclic graph is going to be created by Ludwig for you. And the outputs of one feature are going to be used as inputs to the other features. You also have a bunch of training hyperparameters, from the number of epochs to the batch size, to the learning rate, and so on, that you can specify. And this allows you, basically, you don't have to write your own training loop. The training loop is written for you and has all these options. Finally, you also have, you can also specify pre-processing parameters. For instance, if you have image features, image can be rescaled to a certain dimension. You can specify what is the dimension of that the images have to be reshaped to. Or if you have text, you want to specify like what the maximum length of the text and how many different words in the vocabulary are we going to use. These preprocessing parameters are generic and apply to all the features of a specific type. For instance, all the text features are going to use these parameters, but you can also specify the same parameters for each single specific input feature. Because for instance, if you have two textual input features, one for the title of a news and the other one for the body of the news, then you can specify different parameters like different lengths for both for both input features, for instance. And this is something that they recently added. Now there's a way to do tokenization and pre-processing of text features in many different languages, and also in a multi-language fashion when you don't really know what the language is, the input that you're dealing with. This is just an example of how you would go and add your own encoders. This is an example of how flexible actually Ludwig is. And you can see you just have to create a class with two functions, init and call. In the init, you can just specify all the upper parameters of this class that you want to use. And in the call, an input is going to be provided to you, which has specific dimensions. In this case, it's a tensor for a sequence of sides, batch times sequence of a type int32. And then you have to provide a tensor as output of dimensions batch times sequence times hidden. And all the code that you put inside, it's your own responsibility. You can add your own fancy new encoder. And all the rest of Ludwig is going to work fine with that, just because this is a common interface that it's going to accept. So let me show you some example models. This is the text classification model that we've seen at the beginning. On the left, you have your the data, and on the right, you have all the command that you need to write in order to train a model on this data. And if you want to do like an image classification, all you have to do is just change the input feature from being text to be image, and it's going to work right away. This is a model that is similar to what we are using internally at Uber for expected time of delivery of Uber Eats. You have the restaurant, which is treated as a category, the order, which is treated as a set or as a bag, actually, and hours and minutes as numerical features. And we're going to predict is a numerical feature for the amount of minutes that it's going to take for this order to be delivered. This is an example of a sequential generator where you have this sequence-to-sequence model where you have the user that is saying something and the second user that is saying something else. And you can train a super simple chit-chat model by just specifying that the first input feature is a sequence or a text, and is going to be encoded by an RNN with a cell type LSTM. And the output feature is again a sequence in this case, and is going to be again decoded using an LSTM. And in this case, it's also going to use attention, which is a way to perform better alignment between inputs and outputs. And this is another example where you have actually tagging. So you have an utterance on the left and a set of tags on the right, where P actually means person, C means CD, and D means date. And what the model is going to do actually is going to classify each single input, also considering all the rest of the sentence. So each single word is going to be classified in one of those classes. And the way you do it in Ludwig, you just specify that the decoder is a tagger instead of a generator, and it is going to work right away. So Ludwig provides you with some additional goodies. So first of all, to install it, it's really simple. You just have to do pip install Ludwig, and it just works. And it provides you with some programmatic interfaces too. If you want to use Ludwig models from code, train them from code, and use them for prediction directly from code. And all you have to do is you have to import this Ludwig model class, and the model class is initialized, the object is initialized providing the model definition, which is a dictionary containing exactly the same information that you have provided in the YAML files that we've seen so far, for instance. And then you have this model, which is initialized, and you can train it on some data that you can provide as data frame, for instance. And after you train it, you can use it with the predict function to obtain predictions on new and unseen data. But if you have a model that you pre-trained before, then you can just call Ludwig model.load and load the pre-trained model. Other nice things is that it integrates well with some of our own internal tools like PyML and AutoTune, but in particular, it integrates well with Horovod, which is an open source project that Uber released for training training deep learning models in a distributed way. And so if you have Horovod working, all you have to do to train a model, Ludwig model using Horovod is to specify --use Horovod, and it's going to train the model in a distributed way on several GPUs on several different machines. I believe the main strength for Ludwig is experimentation. So the fact that you can plug in your different models, both for encoders and decoders and combiners, and just change in your model one string to use either of the new things that you added, makes it so that you have a really concise and really well-defined experimental setting, and that can be used for comparing different models and experimenting with models really easily. And in particular, it can also be used for hyperparameter optimization. I don't want to get into the details of this, but on the left side, you have an example of one model, basic model definition. And on the right side, you have an example of some hyperparameters that we want to optimize. And so you just specify the ranges, and several samples are going to be drawn from these distributions, and several models are going to be trained in parallel. And the performance are going to be collected in one place so that you can analyze all of them. And that one place is actually an output directory that contains the predictions, the training statistics, and the test statistics. And those are useful because there are a bunch of visualization commands that you can use that basically provides you with a bunch of different visualizations from those outputs without you having to write anything, actually. And these are just some examples. For instance, we have a comparison of different models on different measures, a calibration plot, a plot that is showing how much the accuracy improves if you increase the threshold on the model's confidence. The middle plot in the bottom is showing a comparison of different predictions of the models when two models are both correct, when one is correct, the other is wrong, and when they're both wrong. And the final one is a comparison of the F1 score for each class as changing the frequency of that class. Ludwig actually still misses a lot of things. This is just has been released like two months ago, and we've been improving it ever since, but we still want to improve it. One direction in which we want to improve it is to add even more input data types. We want to have speech, we want to have videos, we want to have point clouds, all these sort of things. We also want to add additional encoders. For instance, the BERT and GPT-2, which are like recently being used for great improvements in NLP tasks, are going to be there in the near future. We also want to add decoders for some of the features that are missing them. For instance, images and time series at the moment don't have decoders, but we're going to add them. And finally, the weakest point in Ludwig at the moment is the fact that it relies on CSVs for reading inputs from disk. We want to integrate with Petastorm, which is another project that was released by Uber as open source that allows you to read data from either CSVs or S3 or from HDFS or directly from Hive queries if you want. And that will allow to train Uber models on petabytes of data without the need to actually work with the limitations of a CSV, of having a CSV file. And so you can see that you can check the documentation on ludwig.ai. I spent a lot of time doing that, writing that documentation. So it's actually, it's pretty rich. So hopefully you can find everything that you need there. But there's also, you can also check directly with the code. It's on GitHub. And there's also a blog post that we released that describes Ludwig in more details. And we're going to release soon enough also a paper, a scientific paper about the nitty-gritty details of the architecture, how it works, and so on. And this is it. Thank you for your attention.